To understand this, let us consider these given values. Suppose x1, x2, x6. This is a random sample of size 10, which is coming from normal distribution with mean mu and variance sigma square. So in this case, 6 observations are given to us and rest 4 are missing. And you have to find out the MLE. So how do we do that? So in the previous example, it was for the general sample, and here we are looking at some specific values. Here, if you first see, if you just let me show you this one. So here, when you have to find out the estimates using MLE, so what we need is summation xi, observed values, and summation xi squares, right? So it means here also I need to first find out what is summation xi. So that is, if you add up these values, you would get 8.46, and summation xi square would give you 15.30. Okay. So in the EM algorithm, we need to initialize theta with some random value from the parametric space. So we denote it as theta old. And in this case, let us assume that this theta old, that is the parameter estimates that are given to us, suppose it is 0.8 and 1, because mu can be from minus infinity to infinity and sigma is positive. So here we are, since these are small observations, we can start with 0.8 and 1. So let us see, how do we do that? Now mu would be what? The formula says that summation xi plus, so I going from 1 to m, so m is 6 in this case, right? So 6 observations are given to us, plus n minus m, mu old. So mu old, what is mu old? Mu old that we have just now assumed that it is 0.8. Summation xi is 8.46, n minus m. So n minus m would be 10 minus 6, which is 4, into 0.8 divided by n. So this is 1.166. Similarly, sigma square nu, we will substitute these values. Sigma square is 1, sigma square old that we have assumed, right? And here you see that we substitute mu nu, because mu nu is already obtained over here. So we substitute that value, that is 1.166. So what we obtain is 0.890. So this is the first iteration. Likewise, we will move on to the second iteration, and we will now treat this 1.166 as the mu old, and this 1.890 as sigma square old. And again, we are going, based on these two values, we are again going to solve what is mu nu in the second iteration and what is sigma square nu in the second iteration. So for the second iteration, we said these, which we have already obtained over here, 1.16 and 0.890. So for mu nu, again we are substituting the values. Rest of the things remain same, only here mu old is changing. It is getting updated for this. It is now 1.312. And sigma square nu, again in this case, these things are getting changed. And mu nu here, it would be 1.312. And you see that this value comes at 0.631. So like this way, the iterations would continue up till the point where the difference between these mu nus from the first iteration and second iteration, or you can say that the difference in k or kth iteration and k minus 1th iteration is very, very less, right? So at that moment, when it is very close, you can define a tolerance level up to which you want, and if it is getting very close, then you terminate the process and you consider that particular mu nu and sigma square nu as the parameter estimates for your distribution, normal distribution. Okay, so this is how your normal distribution EM algorithm works. Now, since I have shown here for the univariate setup, likewise, it is more useful when you have multivariate or you have the multi-normal distribution in that, or the multivariate normal distribution. In that case, it is very much helpful. Likewise, the second most common example that we encounter is for the binomial distribution. Okay. When we encounter binomial distribution, so there we have usually consider the multinomial distribution. Okay. So here we are just considering this one, the simpler one, binomial one, so that you understand it clearly. So the third example is if you have a complete data vector x1, x2, xm which is coming from binomial k, the parameters are k and p. So here we are not taking np because n is already as the sample size, so we are using a different notation. So based on this you can write this likelihood over here, right? Because we know that the PMF is n choose x or k choose x. So it is basically k choose x, p raised to the power x, q raised to the power n minus x, right? So in this case it would be, sorry, this is k minus x. So when you write the likelihood function, it would be a product of these independent PMFs. So here you have p raised to the power summation xi and 1 minus p raised to the power n times k minus summation xi. And if I have to write the log of this, so we will basically have log of this plus summation xi log p would come. And again, this one would be nk minus summation xi 1 minus p, log of 1 minus p. Once you have this likelihood function, log likelihood function, we write the E step. And in E step, we take out the expectation of this log likelihood function. So when we take out expectation, we are considering that the observed data is given to us and the old estimate P old is given to us. Okay. So here you see that this is the step that we have just simply written, and now we have substituted the value over here. Okay. That we obtained the log likelihood function we obtained just now in this case. So we have substituted it. Now we will take expectation inside for each of these terms. There are 3 terms over here. When you take expectation inside for this term, you can keep it as it is for now. Let us look at what happens when we take expectation for the second and the third term. So for this, let me insert a blank page over here and see how it can be done. So the first thing is expectation of, so log p would be there. Okay. So let me just look at expectation of summation xi, where I goes from 1 to n. So it is basically expectation of summation xi, I is from 1 to m plus I is from m plus 1 to n xi. So this one would be, this is again, these are the observed values, so these are given to us. So this would be simply I1 to m xi's. Okay, and you will be left with the remaining ones. So it would be n minus m times expectation of xi. So now each of these xi's is following binomial with parameters k and p. It means that for binomial, expectation of x is basically np, right? So in this case, it would be kp. So here what we get is summation xi I1 to m plus n minus m times n minus m times expectation of xi. So instead of that, it will be kp, and I can write kp old over here. Okay, so this is the same thing that you have obtained over here if you see. Likewise, if you consider the second term over here, k minus summation xi log of 1 minus p. So let us again, log of 1 minus p. So here it is not visible, so it is log of 1 minus p. Log of 1 minus p comes out as it is. Let us look at expectation of this term. So we have expectation of k minus summation xi, where I goes from 1 to n, right? So expectation of, sorry, it would be nk. Here I think, yeah, here it is nk. So here n is missing, so this would be nk. Okay, so you can make this change over here. This is basically nk. So nk is constant, it comes outside, minus summation I1 to m xi minus summation m plus 1 to n expectation of xi's. So this one would be nk minus summation xi, I goes from 1 to m minus n minus m times expectation of xi again would be k times p old. Okay, so you have substituted it over here. So you can see that we have nk minus summation xi. So same thing you are having over here. Okay, So you are done with your E step, and now we have to move on to your M step, where we differentiate it with respect to P. Okay, so in order to differentiate it with respect to P, you can see that here in the first step, here it is basically independent of P, so that will go away. And we are left with log P over here, and this term log 1 minus P. So we have to differentiate the second and the third terms. Okay. So if you can, okay, let me just write it coming to M step. Okay. So let me first write whatever we obtained. So it is summation xi, I goes from 1 to m, right? Plus n minus m times kp old log p. So I'm not writing the remaining terms, so I'm just focusing on those which are already having p, because anyhow the other terms would be 0 when we differentiate it with respect to p. This whole term is log of 1 minus p. So now I have to differentiate it with respect to p and equate to 0. So when I differentiate the first term, so what we have is, so summation xi, I from 1 to m, plus n minus m times kp old, this one, here you will have p, minus would come here, this entire thing would be there, and 1 minus p, because p over here is with minus sign. Now you have to equate it to 0. Basically, when we equate it to 0, some terms would cancel out. So let us do and see how it happens. So here you will have 1 minus p times of this entire thing, right? Summation xi plus n minus m times kp old. Okay. And here again, p times, you would have these remaining terms that you had here, nkp and all those things. This would be equated to 0. And when you solve these terms, basically what you see is, finally you will get summation xi. So the terms would cancel out because there are a lot of common terms. So summation xi plus n minus m times kp old would be finally present, nkp. So from here, when you solve this, what you get is p hat, that is basically summation xi from 1 to m plus n minus m times k p old whole divided by nk, and that is your parameter estimate over here. Okay, so instead of just having x bar, right, in binomial you had x bar, right, as the MLE. So that is summation xi by n. So instead of summation xi by n, here you can see summation xi by k, you could say, but here you see that you have certain extra terms also. And that is why it is important that you pay attention to how your data set looks like and what are your missing observations, and then you deal with it properly. So likewise, we can consider these random sample, which is coming from binomial 5p, that is k is given to us as 5, and the realizations are in this way. So you are given with 8 observations and 4 are missing in this case. So if you see from here, we need summation xi, right? And we need n minus m. So n is the total number of observations, m is the available ones or the observed ones. Okay, so summation xi is 22. And we initialize it with 0.3 because parameter estimate p is the probability of success, so it could lie between 0 to 1. So we have just taken it 0.3. So if we substitute it in the first iteration, what we get? Summation xi, we know that it is given to us n minus m because n is 12, 8. Then 5 is there, k and p old. Nk would be 60.47 you get. Okay. In the next iteration, this P new would become your P old, and P new would again be here. Same values would be there, but this would come over here, and it is 0.5. So 0.47, 0.5, and finally you will keep on doing these iterations until you reach to a point where the difference between these estimates that you are obtaining is very, very less, right? And that moment you will stop and terminate the process. So this is how your EM algorithm works. So whenever you have missing observations in your data set and you are interested in estimating the parameters, then you can use this. We will also see how it is done using your Python. In that case, we will see how it is terminated finally. You have a tolerance level and then you terminate it for that. So all those things will be seen there.